Hello my friends and welcome back to the You Can Do TV channel. Dripping machine efficiently separates the core from the jacket of scrap armored cables. Capable of handling wires ranging from 60 to 200 millimeters, it offers a daily output of 2,000 to 10,000 kilograms and operates with ease. The Guidetti Wire Pro Cable Recycling Plant at Rewold offers an efficient and clean solution for recycling electric cables, radiators, and aluminum cans. This multifunctional system processes both copper and aluminum wires, including flexible and rigid cables, and even radiators. The plant is designed to optimize recycling processes, ensuring that the copper extracted from the cables is of high purity, ready for reuse as raw material. One of the key innovations of this plant is its compact and versatile design, requiring minimal space for installation. The system operates with low energy consumption per ton of cable processed and features reduced operating and maintenance costs. Additionally, it is highly soundproof, with some of the best noise reduction capabilities in the field, ensuring a quieter working environment. The plant is equipped with several optional components to enhance its performance, such as a magnetic separator to recover metal fragments and a conveyor belt system to streamline material handling. It also includes a dry separation table for efficient separation of metals and a metal dust recovery system to capture and recycle fine particles. The mill is easily extractable for quick maintenance, further boosting operational efficiency. Copper mold production is a critical segment of the manufacturing industry, especially in the steel and foundry sectors. Molds made of copper alloys are essential for continuous casting processes, where molten steel or other metals are cooled and solidified into usable shapes. Copper is favored in this application due to its superior thermal conductivity, resistance to corrosion, and ability to withstand the high temperatures involved in metal casting. The global market for copper-based molds, particularly in steel casting, has been growing steadily. According to a report by Grand View Research, the global market for continuous casting molds was valued at around $1.7 billion in 2023, with projections for continued expansion at a compound annual growth rate, CAGR, of 4.2% through 2030. The increasing demand for high-quality metals and alloys, particularly in the automotive, construction, and manufacturing industries, drives this growth. Copper alloys, such as copper nickel and copper chromium, are commonly used in mold production. These alloys are preferred for their high wear resistance and excellent thermal properties, enabling efficient heat dissipation during the casting process. Molds typically have a service life ranging from 6 to 12 months, depending on the casting volume and quality of copper alloy used. Production processes for copper molds involve several steps, including precision casting, machining, and finishing. The molds are often manufactured to very tight tolerances, with diameters ranging from 150 millimeters to over 2 meters, depending on the size of the casting operation. In large-scale operations, molds are typically produced in batches, with some facilities capable of manufacturing up to 1,000 molds per year. Key players in the copper mold production industry include companies specializing in copper alloy manufacturing, as well as those involved in the development of molds for various industries. With technological advancements and a shift toward more sustainable production methods, the copper mold production industry is poised for continued growth, driven by both increasing industrial demand and innovations in material science. The production process for copper mold tubes, continuous casting machines, and continuous milling equipment involves several precise and advanced manufacturing steps. For copper mold tubes, various tapers such as single, multi, parabolic, and convex are designed and produced based on plant-specific requirements. The tapers undergo rigorous testing to ensure quality, with each tube tested under equivalent conditions to validate its performance. For continuous casting machines, the process begins with the design and production of high-speed casting lines, where the molds are carefully crafted using high-precision CNC machining. The machines are built to ensure a seamless flow of molten steel, with features like liquid level detection and quality tracking systems integrated into the production. Continuous milling equipment is produced using specialized technology that supports high-precision operations. The entire process is supported by strict quality control at every stage, ensuring the final products meet the industry's demanding standards. The wire and cable industry is a vital sector within the global economy, valued at approximately $260 billion in 2023, with projections to exceed $300 billion by 2030, growing at a CAGR of 4.3%. This growth is driven by rising demand across industries such as energy, telecommunications, automotive, and construction. Energy cables dominate the market, accounting for nearly 40% of total sales, primarily due to the global transition to renewable energy. For instance, the wind power sector utilizes vast lengths of medium and high voltage cables, with offshore wind farms like the Nordsee One requiring over 100 kilometers of submarine cables. The push for smart grids further accelerates demand for specialized cables. The telecommunications sector follows closely, representing 25% of market share, fueled by the rollout of 5G networks and fiber optic technology. The global optical fiber market alone is forecasted to grow at 8.5% CAGR, with annual demand exceeding 600 million kilometers of cable by 2027. In automotive applications, the rise of electric vehicles, EVs, is reshaping cable requirements. EVs use approximately 25 kilograms of wiring per vehicle, more than double that of internal combustion engine vehicles, driving demand for lightweight, high-capacity cables. Regionally, Asia-Pacific leads the market, contributing over 50% of global revenue, with China producing 60% of the world's cables. In contrast, North America and Europe are hubs for innovation in high-performance and environmentally sustainable cables, with initiatives to reduce lead and PVC use by 30% by 2030. The manufacturing begins with coil forming, where the base structure of the coil is prepared. This is followed by section binding of the coil stack to ensure stability. The process continues with coil shaping, achieving the precise geometry required for optimal functionality. Lead and outhang taping adds protective layers to exposed areas, enhancing durability. Next, machine taping of the main wall insulation applies the insulation system, which combines film, mica paper, and unidirectional glass bound with acrylic resin. The coils are then fitted into a replica stator for accurate final pressing and testing. Key steps like checking tolerances, tan delta, high pot, and interturn testing ensure dielectric integrity and performance. Final quality control verifies compliance with stringent standards. The cured but flexible coils, featuring Class F 155 degrees Celsius capability for voltages above 6.6 kV, are vacuum-packed in moisture-proof bags and secured in heavy-duty wooden crates for export. The flexibility of the end winding simplifies installation, making high flex ideal for large two-pole windings and in situ rewinding without the need for baking, VPI, or impregnation. The high-flex high-voltage coil insulation system by Houghton International is an advanced, fully cured, and flexible insulation solution designed for high-performance electrical applications. The synchronous condenser production industry plays a crucial role in stabilizing power grids worldwide, particularly as renewable energy sources like wind and solar increase their share of electricity generation. Synchronous condensers are large, rotating machines resembling electric generators, but they do not produce power. Instead, they stabilize voltage, provide inertia, and help regulate reactive power in the grid. Market dynamics. The global synchronous condenser market was valued at approximately $550 million in 2023 and is expected to grow at a CAGR of 4.5%, reaching around $750 million by 2030. This growth is fueled by increased investments in renewable energy integration, particularly in regions like North America and Europe. Production scale and facilities. Manufacturing synchronous condensers requires advanced facilities for machining, assembly, and quality testing. A typical condenser weighs between 30 and 80 tons and operates at speeds ranging from 500 to 1,500 RPM. Production centers often have a capacity of producing 30 to 50 units annually, depending on size and complexity. Materials and processes. Key materials include high-grade steel, copper, and specialized insulation for windings. The production involves processes like precision machining of rotors, stators, and housings, followed by high-speed balancing tests and heat treatment to ensure durability. Each unit undergoes rigorous testing to meet IEEE and IEC standards. Applications and demand drivers. Demand for synchronous condensers is driven by the decommissioning of thermal power plants, which traditionally provided grid inertia, and the increasing penetration of variable renewable energy. For example, in Australia, the 2030 renewable energy target has spurred investments in synchronous condensers, with installations adding over 2,500 MVR of reactive power capacity in 2024 alone. With their critical role in modern grids, synchronous condensers are set to remain a pivotal technology, enabling the energy transition while ensuring grid stability. The production of brass instruments at Mirafone follows a meticulous process that blends traditional craftsmanship with modern technology. Located in Waldkraiburg, Germany, Mirafone has upheld its high standards for over 75 years. Material selection and preparation. The process begins with the careful selection of high-quality brass alloys. These materials are chosen for their acoustic properties and mechanical strength. Brass sheets and tubes are delivered in precise dimensions, which are then cut, annealed, and prepared for shaping. Annealing involves heating the metal to make it more malleable, ensuring easier shaping without compromising strength. Bell formation. The bell of the instrument, a critical component for sound projection, is crafted using a combination of hand hammering and hydraulic pressing. Initially, the brass sheet is formed into a cone and soldered along its seam. Skilled artisans then hammer the bell by hand to refine its shape, a process that can take several hours depending on the instrument's size. Hydraulic presses are used for final shaping, ensuring consistency across different models. Valve and slide production. Mirafone's precision valves and slides are produced to exacting tolerances. Valve casings are machined from solid brass cylinders, ensuring a smooth surface for reliable operation. The pistons, once machined, are lapped by hand for an optimal fit. Similarly, the tuning slides are manufactured with minimal clearance, ensuring smooth adjustment while maintaining airtightness. Each valve and slide undergoes rigorous inspection to guarantee proper alignment and responsiveness. Assembly. Once the major components are ready, the assembly process begins. The bell, lead pipe, valve block, and tubing are carefully aligned and soldered together by hand. Highly skilled workers ensure that all parts fit precisely to achieve the desired intonation and playability. The assembly process is followed by a meticulous inspection to check for any imperfections. Surface finishing. After assembly, the instruments are polished and prepared for lacquering or plating. Polishing is done in multiple stages, first with coarse abrasives and then with finer ones to create a smooth, mirror-like surface. Lacquering or silver plating is applied to protect the instrument from corrosion and enhance its appearance. This step is carried out in a controlled environment to ensure a flawless finish. Final testing and quality control. Each finished instrument undergoes a series of tests conducted by expert musicians and technicians. Intonation, response, and tone quality are thoroughly evaluated. Any adjustments needed are made at this stage to ensure the instrument meets Mirafone's exacting standards. Only after passing all tests is the instrument approved for sale. A legacy of craftsmanship. Mirafone's production process exemplifies German precision and craftsmanship. With a focus on quality and attention to detail, each brass instrument reflects the company's commitment to excellence. By combining time-honored techniques with modern technology, Mirafone continues to serve the global music community with instruments renowned for their reliability, sound quality, and ease of play. This dedication to craftsmanship has solidified Mirafone's position as a leading manufacturer of high-end brass instruments. Whether it is a tuba, euphonium, or trumpet, musicians worldwide trust Mirafone for instruments that deliver exceptional performance on every stage.
In Hamburg's industrial heart, steel comes alive, molten, shaped, transformed. ArcelorMittal Hamburg runs the only direct reduction plant in Western Europe, turning iron ore pellets into sponge iron using natural gas, not coal. Cutting carbon dioxide emissions by 40%. That's a big deal. Inside, electric arc furnaces melt sponge iron and scrap at 1,600 degrees Celsius, while robots analyze samples in real time. Liquid steel flows into casting machines, forming red-hot billets. These billets, still glowing, race through rolling mills, stretching into high-grade wire rods up to 100 meters per second. Automated lines coil, cool, and label each bundle with pinpoint traceability. Every stage, from raw ore to precision-wound steel, is tracked, tested, and tuned for quality. This isn't just steelmaking, it's industrial choreography at its finest. Nordex doesn't just build nacelles, it re-engineers how they're made. By shifting from static dock assembly to continuous flow using friction-driven rails, they kept production running while tripling output from 330 to around 1,000 turbines a year. The facility is divided into 6 synchronized lines, each dedicated to a major component: machine frame, generator supports, drivetrain, hub, and pitch systems. These components are moved on skid platforms fitted to friction-driven rail tracks, allowing steady transport without cranes or forklifts. Just-in-time supply chains feed materials directly to workstations, minimizing floor storage. Every station follows standardized procedures, enabling continuous motion with minimal delays. Even during the transition, operations didn't pause, a rare feat in heavy manufacturing. What happens when shipbuilding meets 3D printing? At Navantia CEFAN, a full-scale rudder blade, 4 meters tall and nearly 3 meters wide, was built using additive manufacturing. The process started with 17 polymer parts printed in ASA, each weighing up to 130 kilograms. These segments were assembled and bonded, simplifying traditional construction methods. A fiberglass intermediate layer was then applied for structure, followed by a sleek carbon fiber coating to enhance strength and finish. Sourcing techniques from outside the maritime sector. This first full-scale prototype weighs around 3,500 kilograms. It's not just a new part, it's a new way to build ships. This progressive die system forms metal parts step by step, trimming and shaping with each press stroke. Next, parts are fed into a vibratory deburring machine filled with ceramic media. As the bowl shakes, thousands of pebbles smooth out sharp edges and remove burrs. The transformation is subtle, but essential for both safety and function. No extra handling, just clean finishes. Inly finished parts are sorted, counted, and boxed. It's satisfying to watch, Precision, speed, and surface perfection, all in motion. This is how steel becomes power. Wheel rims for tractors, harvesters, and construction machines are built here with remarkable precision. Each day, tons of certified steel arrive, tagged for full traceability. Flat sheets are straightened, cut, and shot blasted to remove debris and improve paint adhesion. Then comes rim forming, 1 centimeter thick steel bends like clay under massive forming machines. Plasma welding at 20,000 degrees Celsius ensures strong, clean joints, verified in the lab and via X-ray. Simultaneously, steel discs are cut using CNC plasma or presses with forces up to 2,500 tons. After forming, holes are drilled, edges ground, and discs are pressed into rims. Over 8,000 configurations are assembled with automated welding lines. Coating is done through cathodic dip painting. Fully automated and eco-friendly, corrosion resistance is tested in salt mist chambers. Some wheels are paired with tires. Others go directly to precise storage systems, awaiting shipment to 70 countries. It's not just a factory. It's a choreography of machines turning raw steel into essential motion. Upgrading steelmaking isn't just about size, it's about precision under pressure. At Voestalpine, 3 160-ton LD converters were replaced with 180-ton units to boost annual capacity to 6 million tons. Each converter swap demanded exact alignment, millimeter-perfect crane lifts, and seamless integration into ongoing operations. The new converters allow higher tapping weights and longer campaign lifespans, improving both throughput and efficiency. The replacement took place without halting other production lines. It's heavy industry at its finest, where timing, power, and engineering collide to reshape capacity. Chain manufacturing, loud, fast, and deeply technical. At this plant in Holyoke, steel alloys are stamped, heat-treated, assembled, and tested for tensile strength, fatigue life, and wear resistance. Laser express cells boost flexibility, while inline vision systems ensure zero defects. It's a tightly controlled process from raw material to final inspection. Solid stuff. Nothing's left to chance. Watch sharp defense take shape. Steel coils feed into the machine, punched into razor shapes, then wrapped around a core wire at high speed. A precision roller system keeps the strip aligned before coiling begins. Each section is twisted, tensioned, and cut automatically, ready for fences and barriers. Comes some kipsu. This is how massive marine propellers take shape. EPS blocks are robot milled into precise patterns, then embedded in sand to form molds. Bronze alloy melts, up to 18 tons per batch, are poured and left to cool. Used sand is reclaimed while the cast propeller moves on to machining and robotic blade grinding. Skilled hands take over for final polishing. Blue fit tests confirm perfection before assembly. Every step blends heavy industry with fine craftsmanship, and the result is breathtaking. Forging strength into every wheel set, this facility builds and repairs axles, wheels, and assemblies for rail and tramway systems. After heat treatment ensures hardness and stability, a lathe peels perfect spirals of metal from the wheel set. Each axle and wheel undergoes precision finishing before final assembly and inspection, following EN and UIC standards with real-time tracking and documentation. Steel shovels with a reputation for never breaking or bending begin their journey as thick steel plates, which are stamped and cut into shape by powerful hydraulic presses. Each blank is heated until red hot, then pressed again to form the iconic shovel curve, a move that always impresses with its raw force. Edges are trimmed and sharpened, sparking as grinders create a fine, tough blade. Next, shovels pass through a quenching bath, locking in hardness, followed by tempering ovens that relieve stress and prevent brittleness. Watching the glowing steel cool so quickly never gets old. After acid cleaning removes surface oxidation, each head gleams, ready for the next phase. Wooden handles are crafted separately, shaped and sanded for comfort before assembly. Once gripped and riveted, the final product feels solid and balanced in your hand. This process really showcases the blend of heat, muscle, and technique behind every finished tool. Few places showcase American manufacturing pride, like the Federal Ammunition Factory. Production begins in the rimfire area, where lead and brass are shaped into cases and bullets. Next comes the shot show line. Molten lead is dropped through screens and water to form perfect shot pellets. In the center fire department, raw brass is crafted into cases filled with custom bullets and loaded for handgun and rifle ammunition. Finally, deep underground, quality control experts test each batch for pressure, velocity, and accuracy. Watching this process, it's clear why Federal is trusted for consistent, high-performance ammunition worldwide. This flow-forming process is designed specifically for our 19-inch XS5 rim, combining precise engineering with automation. Each aluminum blank is loaded onto a blue conveyor and prepared for pressing. Every step feels like a build-up to something special. Hydraulic presses give the rim its initial shape, then it's swiftly transferred into a quenching tank. The rush of steam as the hot metal meets water marks a key stage in strengthening the alloy. A robotic arm then lifts the rim onto a spinning mandrel, where the real transformation unfolds. Flame torches heat the edge while rollers press and stretch the rim, forming the exact profile needed for the XS5. Maintaining perfect temperature and pressure is critical, ensuring every rim meets the performance standards required for modern wheels. Watching the sequence, the hiss of water, bursts of flame, rollers working in harmony, you can really appreciate the technology behind the XS5. In the end, each 19-inch rim stands ready to deliver strength, lightness, and style on the road. This is engineering you can see in action. The H6 Machining Center carves tough herringbone gears from SM45C steel with impressive speed and accuracy. Twin drives and box guideways keep every cut stable. Watching this precision in action is truly satisfying. Every casting starts with carefully prepared sand molds, shaped by hand and simple tools. Workers press and carve the sand, making sure every cavity and detail is just right. There's a special focus as they set the cores and reinforce the mold, knowing that any mistake affects the final product. Next comes the molten metal. glowing orange, intensely hot, and flowing smoothly as it's poured into the waiting molds. The air fills with heat and anticipation, each pour demanding steady hands and quick reactions. Foundry work is a real test of attention and skill. Watching the metal fill every corner of the mold, you can't help but respect the craft and tradition behind this process. High-speed drilling lines like the Endeavor 1203DD transform steel beams with precision and efficiency. The process starts by loading massive profiles onto the line, where direct drive spindles quickly position for each hole. Automated clamps lock the beam in place as powerful drills cut through the steel with impressive speed. Every movement is monitored for accuracy, ensuring perfect results. It's amazing to see such robust machinery deliver consistent, high-quality holes ready for assembly in modern construction projects. Linear friction welding joins metal parts by rapidly rubbing them together under pressure. Sparks fly, surfaces fuse, and the result is a super strong bond, perfect for aerospace applications. The process here is remarkable. Bimatech Soralushi's machining centers showcase serious engineering power and versatility. The T-Series features compressed bed milling and boring centers built for accuracy and stability on the toughest parts. The S-Series uses rigid beds for powerful milling and drilling, handling even challenging materials with ease. The F-Mount series combines milling up to 4 meters with integrated turning and grinding, making it ideal for large, complex components. For flexibility, the F-Series offers moving column milling centers, allowing for long workpieces and dynamic operations. It's impressive to see how these machines adapt seamlessly from small toolmaking to machining massive industrial parts. Large part machining can run in shuttle mode, with workpieces shuttled in and out for non-stop productivity, or on machines with movable tables or gantry designs for maximum adaptability. The VTC series stands out with carousel turning and milling centers, enabling efficient multi-face machining without repositioning. Watching these high-precision centers in action, you can truly appreciate the blend of innovation and reliability behind every design. Each innovation reflects Soralus's commitment to quality and versatility, empowering manufacturers to push the boundaries of what's possible in modern engineering. Step 1 in making a Vanquet wheel starts right here. An aluminum disc spins rapidly between 2 heavy rollers. Under controlled pressure, the metal stretches and curves outward, gradually taking shape as a rim half. It's mesmerizing to see how the rollers guide every detail. Precision in this stage is critical for building a strong, reliable wheel that performs on the track. Tube bending at Goodfabs is a masterclass in precision and technique. Inconel tubing is clamped in place as the mandrel bender smoothly curves it without wrinkling or collapsing the walls. Each bend is carefully monitored, and the tooling selection is impressive, handling diameters from 1 to 3.5 inches across various center lines. The shine of freshly bent inconel is seriously satisfying, hinting at the performance applications ahead. Technicians' expertise ensures that every exhaust part meets the strict demands of Formula One teams and top engine builders.
The production of faucets is a complex process that transforms raw materials into high-quality bathroom fixtures. Below is a breakdown of the process: manufacturing of molds. The journey begins with the creation of precise molds, which serve as the foundation for casting. These molds are crafted with high accuracy to ensure the final product meets stringent specifications. Raw materials and sand core manufacturing. The production relies on top-quality raw materials. Sand cores are then manufactured to create internal cavities in the faucet, which will allow water to flow through. Casting. Molten metal is poured into the molds, taking the shape of the desired faucet design. This process demands precision to maintain structural integrity and aesthetic appeal. Demolding and cutting. Once cooled, the cast faucets are removed from the molds. Excess material is carefully cut away, leaving the basic structure of the faucet. Machining. The faucets undergo machining processes to refine dimensions and create threads or other functional features. This ensures compatibility with plumbing systems. Quality control. Each piece is inspected to verify dimensional accuracy and structural soundness before moving forward. Grinding and polishing. The surfaces are ground to eliminate imperfections and polished to achieve a smooth, flawless finish. This step significantly contributes to the faucet's visual appeal. Chrome plating. The polished faucets undergo chrome plating, a critical step that provides corrosion resistance, durability, and a brilliant finish. Inspection and cartridge manufacturing. Every piece is inspected for defects. Simultaneously, cartridges, the essential components for controlling water flow, are manufactured. Assembly. The various components, including the cartridges, are assembled into a complete faucet. Final quality control and packing. A final quality check ensures the faucet's performance and aesthetic standards are met. The finished products are then packed and prepared for distribution. Matazel Foundry specializes in the production of die castings using aluminum and zinc alloys. The process begins with the preparation of materials, followed by die casting under high pressure. Precision CNC machining is then employed to refine the castings, ensuring tight tolerances and high-quality finishes. To further enhance product quality, the company performs comprehensive laboratory testing and measurement services. The entire production process is supported by advanced machinery and a skilled technical team, ensuring efficiency and consistency from start to finish. The production of SVIS trade brass fittings is rooted in precision engineering and meticulous craftsmanship, reflecting Czech expertise since 2011. The process begins with the selection of premium-grade CW617N brass, renowned for its strength, corrosion resistance, and compatibility with drinking water. Raw brass is transformed through advanced machining and forming technologies, ensuring each piece meets stringent quality standards. The fittings are crafted in multiple series, each tailored to specific applications, from robust construction to quick coupling solutions. Threading and sealing are achieved with high-precision tools to ensure secure and leak-proof connections. The fittings undergo rigorous quality checks, including dimensional inspection and pressure testing, to guarantee reliability under varying conditions. Surface treatments and coatings are applied for enhanced durability and aesthetic appeal. The fittings meet stringent European standards, providing safe, reliable solutions for plumbing and piping systems. Every step in production, from design to packaging, is optimized for efficiency and excellence, upholding the company's reputation for high-quality brass fittings worldwide. The LPG valve, 20-kilogram auto-assembly machine is an efficient system designed for automated assembly with a focus on speed and precision. The process begins with the loading of valves onto trays, each tray capable of holding 32 valves. These trays are transported to the machine using a cart, with each cart accommodating up to 10 trays. Once loaded, the trays are processed through the system, where the components undergo precise assembly operations in a highly controlled manner. After assembly, the finished valves are automatically unloaded onto a conveyor for subsequent handling or packaging. Empty trays are reloaded onto carts in batches of 10 trays per cart, ready for reuse in the cycle. The machine operates with a remarkable cycle time of 4 seconds per assembly, ensuring high throughput and productivity. This system integrates seamlessly with upstream and downstream logistics, making it ideal for large-scale manufacturing environments. Its automated loading and unloading processes significantly reduce manual labor while enhancing operational efficiency and product consistency. Powered by an AC220V, 3-phase, 60 Hz electrical supply, and using compressed air at 5 to 6 kilograms cm squared. This machine is controlled via a programmable logic controller, ensuring smooth and accurate operation.
A new chapter in aerospace manufacturing. This is the multifunctional fuselage demonstrator. Watch how automation and composite innovation shape the upper shell layer by layer. Using in-situ consolidation, 53 kilometers of thermoplastic tape form the fuselage skin. 44 compression molded stringers are robotically spot welded every 500 millimeters. Next, 24 carbon frames are aligned manually, then resistance welded into position, around 300 welds in total. Finally, 158 cleats are installed using cobot-guided precision. Every process here is optimized for speed, strength, and sustainability. Impressive? Absolutely. This is how lightweight aviation becomes a reality. It starts with a solid chunk of brass and ends with precision-engineered parts that shine like gold. CNC machining transforms this dense metal through a symphony of movement. First, the raw brass is clamped into the chuck, and the cycle begins. A rotating spindle carves away layer after layer, revealing clean contours and tight dimensions. Flat end mills sweep across the surface, shaving off material in controlled paths while following a pre-programmed toolpath with pinpoint accuracy. Drills plunge with micrometer accuracy. Threads are cut, slots are milled, and every pass of the tool is calculated. It's mesmerizing to watch. The rhythmic whir, the sharp tool changes, the gleam of polished brass. Every part is held to strict tolerances, often within a few thousandths of an inch. The machine doesn't tire, doesn't flinch, just cuts, measures, repeats. From prototype to production, brass machining like this proves how beauty and precision can coexist in metal. This 4-column hydraulic ring cogging press reshapes red-hot steel ingots into massive forged rings. The glowing billet is placed beneath the ram, where each stroke compresses and elongates the metal. The material is progressively worked, not in one hit, but through calculated, repeated force. Between presses, operators rotate the part to ensure uniform forming across the ring. The process is as physical as it is precise, metal flowing under pressure, slowly forming its final shape. These rings aren't decorative. They're destined for turbines, heavy-duty bearings, and critical machinery. Every forged curve tells a story of power, control, and the importance of getting it exactly right. Forging is carried out in high-grade steel dies, machined for repeatable tolerances. Steel bars are heated until glowing, then forged in CNC-shaped dies. These parts, power machines, vehicles, and tools. Built to perform, built to last. You can almost feel the impact through the screen. Wing removal on an F-16 isn't routine, it's a coordinated teardown. At the fuel barn, technicians first disconnect hydraulic lines and wiring, securing every system. Bolts are removed, jacks stabilize the fuselage, and the damaged wing is lifted out. A replacement is carefully aligned, torqued down, and reconnected. Every connection is re-verified. This is maintenance with zero margin for error, one wing at a time. Steel casting comes alive in Stoke-on-Trent, where heat, force, and skill converge. Inside Goodwin steel castings, molten steel churns with power inside an electric arc furnace. Once refined, it's tapped and poured into robust molds, built to handle the extreme heat and weight. After solidifying, the casting is removed and prepared for machining. At the machine shop, large components are milled, drilled, and shaped to meet tight tolerances. Non-destructive testing verifies internal soundness, while precision checks confirm each part is production-ready. This process combines heavy industry with exacting standards. It's not just molten metal. It's structured force, skillfully directed, and precisely delivered. This is no ordinary turning center. It's the Doosan Puma SMX 2600ST, taking on a landing gear component with confidence and control. It begins with a solid steel bar locked in place. The spindle spins up, and rough turning removes bulk material in heavy passes. Then, the multitasking begins. With Y-axis milling and live tooling, the machine shapes grooves, bores, and threads, all in one continuous setup. No reclamping needed. Each transition is seamless, minimizing error and maximizing precision. The tailstock supports the workpiece throughout, reducing vibration. Coolant jets keep temperatures in check, ensuring tolerances stay tight. As internal features are cut, the machine automatically swaps tools, adapting for each function. Watching it work feels like watching engineering choreography, synchronized, controlled, exact. This isn't just cutting metal. It's crafting structural reliability for high-stress aerospace applications. "3D sand printing is changing the way engine blocks are made, and it's incredible to watch. The process begins with a large-format industrial printer layering resin-coated sand, one ultra-thin sheet at a time. Guided by a digital model, the printer forms a complex mold, complete with intricate channels for coolant and lubrication. Each pass fuses the sand with binder, building the mold from the ground up with no need for traditional tooling. No cores to align, no assembly required. Once complete, the mold is cleaned and prepared for metal pouring. This level of freedom in mold geometry means lighter, more efficient engine blocks. Plus, lead times are dramatically shorter. There's something captivating about watching dry grains of sand become a detailed engine mold with no tooling at all. Watch raw minerals become high-end sintered stone. The process starts with sieving fine powders, then moves to a 30,000-ton Sacmi press from Italy, compressing material under extreme force. After forming, digital inkjet printers add intricate textures. Finally, a cloud-controlled roller kiln fires each slab with perfect consistency. It's tech and pressure, art and fire, all converging to create durable, stunning surfaces that redefine modern interiors. Watch copper separation at its finest. Cathode plates are lifted from electrolytic cells and loaded into the system. High-pressure water jets remove residual electrolyte using custom-designed nozzles. The plates move through bending and stripping, releasing pure cathode copper. Each sheet is flipped, embossed, weighed, and stacked automatically. Meanwhile, stainless plates are inspected and either recycled or rejected. It's fast, clean, and endlessly repeatable. Watch waste become worth. Sugarcane bagasse transformed into everyday packaging. It all begins with raw pulp made from bagasse and bamboo fibers. Softened, mixed with water, and filtered to form a smooth slurry. This pulp slurry is then pumped into forming molds. Suction removes excess moisture. Once shaped, the wet molds enter a hot pressing station. Heat and pressure lock the structure into place. The finished containers are automatically stacked and conveyed, clean, strong, and compostable. It's sustainability in motion. Heat, force, rotation. This is how giant steel rings are born. The billet is first heated until it glows, then forged into shape with immense pressure. A mandrel and rollers expand it outward, transforming thickness into diameter. This hot rolling process demands precise coordination. Each rotation stretches the metal evenly. You can feel the force in every turn. Massive, glowing, unstoppable. This gear isn't just heated, it's transformed. The FlexScan induction scanner applies high-frequency electromagnetic fields to heat only the surface, hardening it while keeping the core tough. The gear is lifted and rotated under the coil, receiving uniform treatment. Immediately after, it's quenched to lock in hardness, then tempered to reduce brittleness. It's a thermal engineering ballet, controlled, repeatable, and efficient. Watching heat treat with this level of precision shows how modern manufacturing turns raw steel into resilient components. This is a billet cutting station in action, processing solid steel bars with speed, precision, and minimal contact. A solid steel billet is set into position, cool and gray, ready for the cut. From the side, a hydraulic arm briefly taps the billet, signaling the start. In one swift motion, the saw blade drops, slicing through the metal with purpose. Cut pieces roll off the table under their own momentum. Sensors track the cycle, optimizing timing and blade performance. It's billet cutting streamlined to perfection. You're not just seeing metal cut, you're seeing process engineering at its smoothest. Steel, sparks, and synchronization. Welcome to Huaheng's automated welding line. Here, factory automation isn't just about robots. It's about efficiency engineered into every second. The process begins with RGV's rail-guided vehicles, delivering steel components directly to the robotic welding cells. There's no manual handoff, no delays, just precise logistics feeding a relentless workflow. Each part arrives pre-positioned into jigs that lock them firmly into place. Then, the robots take over. One arm moves in to perform spot welding, fusing metal joints in milliseconds. Another arm follows with arc welding, creating deep, strong bonds along structural seams. Multiple robots operate simultaneously. The timing is coordinated to the second, every motion tuned to the line's rhythm. Even the torch angles are dynamically adjusted to match joint complexity. It's smart welding, not just strong welding. Sensors monitor every weld in real time. Heat, alignment, and spark patterns are continuously adjusted to ensure strength and accuracy. Between cycles, the welding guns are automatically cleaned and prepped, reducing downtime and keeping quality high. The RGV system continues moving. New parts in, completed frames out. Efficiency doesn't pause here. It loops, optimizes, and accelerates. From chassis frames to complex assemblies, this line produces high-volume, high-precision welds without compromise. Watching this process unfold shows just how far industrial fabrication has evolved. Precision, speed, and coordination in every movement. It's not just automation, it's controlled intensity, delivering repeatable results with machine-level confidence. Molten slag doesn't go to waste here. At Harsco, steel slag is handled with purpose. From collection at the furnace to cooling, crushing, and metal recovery. Each step turns byproduct into resource. It's sustainability in action, transforming waste into usable material. This video walks you through how classic paper shot shell hulls are made. It starts with a 250-pound roll of paper, scored, re-rolled, and shaped into 12-inch tubes. After drying, each tube is lubricated, sized, and conditioned before being cut into 3-inch hulls. Every step leads to a durable, high-performance shot shell made to crush clay with power. Here's how 9-leg plastic trays are formed using a hollow blow molding machine. First, molten plastic is extruded into a parison, like a glowing tube of soft material. The mold closes around it, and compressed air inflates the parison to fill the mold's contours. You can see the tray take shape almost instantly. Once formed, the mold opens. and the newly shaped tray is ejected. The machine cycles again: parison, mold, air, tray, fast and consistent. It's fascinating to see how precision and timing turn melted polymer into stackable, durable trays. Blow molding at this scale feels like watching material obey pure mechanical choreography. Installing a TC rotor on a large vessel isn't just routine. It demands exact alignment. Watch how technicians carefully guide the rotor into place. Every millimeter matters in a fit this tight. Installing a TC rotor during large-scale repair demands both skill and coordination. Precision alignment is key. The rotor must fit exactly into its casing to ensure optimal rotation, load balance, and thermal performance under full operational stress. From solder paste to signal testing, every smartphone begins long before you touch the screen. At OPPO's Chongqing factory, the journey begins with surface mount technology. Solder paste printing, component placement, and precise calibration. Fluids are dispensed, chips aligned, and the board comes to life. Next comes the assembly stage: battery, camera, IMEI tagging, and antenna testing. It's fast, automated, and exact. Every part, every connection, engineered for performance, inspected for perfection. This is smart manufacturing in action. From wax to metal, this is how precision parts are made. At Pennsylvania Precision Cast Parts, investment casting begins with wax injection, forming patterns that match exact part dimensions. These patterns are grouped, coated with ceramic, and fired to create tough molds. Then, molten metal, up to 3,000 degrees Fahrenheit, is poured, cooled, and broken free. After cutting, polishing, and heat treating, parts are tested and inspected before packing. Each step is engineered for accuracy, making this process ideal for high-spec components across multiple industries.